Hey everyone, how goes it? And welcome back to Computer Science 311. Today, we're going to talk about synchronization tools. A system typically consists of several, perhaps hundreds or even thousands of threads running either concurrently or in parallel. Threads often share user data. Meanwhile, the operating system continuously updates various data structures to support multiple threads. Process synchronization involves using tools that control access to the shared data in order to avoid conflicts. Now we establish that a cooperating process is one that can affect or be affected by other processes executing in the system. A cooperating process can either directly share logic address space or be allowed to share data only through shared memory or message passing. Concurrent access to shared data may result in data inconsistency. In order to maintain data consistency, we need to have mechanisms that make sure that the orderly execution of these processes will not affect it. In this example, we have two processes, P0 and P1, that are creating a child process using the function fork. Now, if we remember back, whenever fork is called, this returns the process identifier for a newly created process. However, in this example, we can see that both of these processes are calling this, so which one gets the next available ID? Will it be process 0 or process 1? This can be very difficult to evaluate, but the answer is whichever process accessed it first. Now, a situation like this where several processes are trying to access and manipulate the same data concurrently, and the outcome of that execution depends on the particular order in which they are accessed, this is called a race condition. The process ID in this case depends on whether or not process 1 or process 0 accessed it first. This can be a very nasty synchronization problem. Now, unless we have a mechanism to prevent this, we can have the same process identifier assigned to two different processes. So now we have to start thinking about process synchronization, and we need to first address what's called this critical section problem. Let's consider a system consisting of n processes going from process P0 to process Pn-1. Now let's assume that each process has a segment of code called the critical section, in which the process may be accessing and updating data that is shared with at least another process. Now with this critical section, we can view the general structure of any process as basically this. What we're worried about is what happens whenever this process enters that critical section. Now, an important feature of the system is that when one process is executing its critical section, no other process is allowed to execute in its critical section. Now that is, no two processes are executing in their critical section at the same time. The critical section problem is to design a protocol that the processes can use to synchronize their activity. This is to allow them to cooperatively share data. Each process must request permission to enter its critical section. The section of code implementing this request is called the entry section. Now, after the critical section, it can be followed by what's called an exit section. Now, the other code is just simply called the remainder section. Now, understanding the entry and the exit section, we could take a look at this general structure for every single process. The process has to execute some sort of entry section to declare that their critical section is about to happen. This critical section happens where no other process is running its critical section, and then it must exit by calling something to declare that it is exiting the critical section. The rest of the code is just called the remainder of this. Now, any solution to the critical section problem has to satisfy the following requirements. First, mutual exclusion. If a process P sub I is executing in its critical section, then no other process can be executing in their critical section. Number 2, progress. If no process is executing in its critical section, and some process wishes to enter their critical section, then only those processes that are not executing in their remainder section can participate in deciding which will enter the critical section next, and the selection cannot be postponed indefinitely. Number 3, bounded waiting. There exists a bound, or a limit, on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. A very classic solution to the critical section problem is called the Peterson solution. Now we restrict this to two processes that alternate execution between their critical sections and their remainder sections. The solution of this requires that two processes share two data items, one called a turn and another called a flag. The variable turn indicates whose turn it is to enter the critical section. That is, if turn is equal to I, then process I is allowed to execute its critical section. The array flag is used to indicate if a process is ready to enter the critical section. So, for example, flag of index I is true if P of I is ready to enter its critical section. So now that we have this in place, we are ready to describe the algorithm. Here is an example implementation of the Peterson solution. To enter the critical section, process P sub I first has to set flag of I to be true, and then it sets the turn value to J, thereby asserting that if another process wishes to enter the critical section, it can do so. If both processes try to enter at the same time, turn will be both set to I and J at roughly the same time. Only one of these assignments will last. The other will occur, but it will be overwritten immediately. The eventual value of turn determines which of the two processes is allowed to enter the critical section first. Now that we've shown that, we have to figure out if this is correct. Before we introduce three criteria in order to solve the critical section problem. It has to have mutual exclusion, progress has to be made, and there must be a bounded weight requirement. Now let's look at all three. Now to prove mutual exclusion exists, we note that each process, P sub I, only enters its critical section if that flag of J is equal to false or the turn is equal to I. By doing this, we can prove that mutual exclusion is preserved so that the critical section of one process is not running while another critical section of another process is currently running. We can also use this to prove properties 2 and 3. Now, while this is a solution to the critical section problem, Peterson's solution is not guaranteed to work on modern computer architectures. The main reason for this is that to improve system performance, processes and/or compilers may need to reorder read and write operations that have no dependencies. For a single-threaded application, this reordering is immaterial as far as program correctness is concerned. However, for multi-threaded application with that shared data, reordering instructions may render inconsistent or unexpected results. As an example of this, let's consider the following data that's shared between these two threads. Boolean flag is set to false, int x is set to 0. Now, as we can see, thread 1 performs a following spinning while loop, that while the flag is not false, it keeps printing the value of x. Thread 2 assigns the value of x to 100 and also sets the flag to true. The expected behavior, of course, is that thread 1 outputs the value of 100 for that variable x. However, as there are no data dependencies between the variables flag and x, it is possible that the processor may reorder the instructions for thread 2 so that the flag is assigned to true first. In this situation, it is possible that thread 1 would output 0 for variable x. Now, less obvious is that the processor may also reorder the statements issued by thread 1 and load the variable x before loading the value of the flag. If this were to occur, thread 1 would output 0 for the variable x, even if the instructions issued by thread 2 were not reordered. Let's consider what happens to the assignment of the first two statements that appear in the entry section of the Peterson solution but are reordered. It is possible that both threads may be active in their critical section at the same time. The only way that we can preserve mutual exclusion is by using proper synchronization tools. Now, what we have described so far is a software-based solution to the critical section problem. However, software-based solutions are not guaranteed to work on modern computer architectures. So now we're going to take a look at hardware instructions that provide support for solving the critical section problem. Now, we have previously seen that the system may reorder instructions, a policy that can lead to unreliable data states. Now, how a computer architecture determines what memory guarantees it will provide to an application program is known as a memory model. In general, a memory model falls into one of two categories. One, strongly ordered, where memory modification on one processor is immediately visible to all other processors, or weakly ordered, where modifications to the memory on one processor may not be immediately visible to other processors. In order to address this issue, computer architectures provide instructions that can force any changes in memory to be propagated to all other processors, thereby ensuring that the memory modifications are visible. Now, these such instructions are known as memory barriers or memory fences. When a memory barrier instruction is performed, the system ensures that all the loads and stores are completed before any subsequent load and store operation is then performed. Therefore, even if instructions were reordered, the memory barrier ensures that the store operations are completed in memory and are visible to all other processors before future load and store operations can be performed. So now let's return to a previous example in which reordering instructions could have resulted in the wrong output. Now we use a memory barrier to ensure that we obtain the expected output. So now if we add a memory barrier operation to thread 1, as we can see here with this while loop, we can now guarantee that the value of the flag is loaded before the value of X. Now similarly, if we place the memory barrier between the assignment performed in thread 2, as you can see there, we then ensure that the assignment to X occurs before the assignment of the flag. Now, with respect to the Peterson solution, we could place a memory barrier between the first two assignment statements in the entry section to avoid the reordering operations. Now, we also note that the memory barrier are considered very low-level operations and are typically used by the kernel developers when writing specialized code that ensures mutual exclusion. In addition to that, many modern computer systems provide special hardware instructions that will allow us to either test and modify the contents of a word or swap its contents of the two words atomically. Atomically in this sense means that it is one uninterruptible unit. We can use these special instructions to solve this critical section problem in a relatively simple manner. Rather than discussing one specific instruction for one specific machine, we abstract the main concepts between these types of instructions by describing the test and set and the compare and swap instructions. Now, looking into this further, the test and set can be defined as we see here. The important characteristic of this instruction is that it is executed atomically. Thus, if two test and set instructions are executed simultaneously, they will be executed sequentially in some arbitrary order. If the machine supports test and set instructions, then we can implement mutual exclusion by declaring a Boolean variable lock. The structure of this process can be seen right here. Now similarly, the compare and swap instruction, just like the test and set, operates on the two words atomically, but use different mechanisms that based on swapping the contents of those two words. The compare and swap instructions operate on three operands and it is defined here. The operand value is set to the new value only if that value is what we expect. Regardless, copy and swap always returns the original value of the variable value. Now, the important characteristic of this instruction is that it is executed atomically. Thus, if two compare and swap instructions are executed simultaneously, they will execute sequentially in some arbitrary order. Typically, compare and swap instructions is not used directly to provide mutual exclusion. Rather, it is used as a basic building block for constructing other tools. One such tool is called atomic variables, which provide atomic operations on basic data types such as integers and booleans. Most systems that supports atomic variables provide special atomic data types as well as functions for accessing and manipulating atomic variables. One example is if we had a sequence and that was an atomic variable, we can have the function increment be an atomic operation on that variable. The hardware solutions to the critical section problems that we have presented are complicated, as well as generally inaccessible to application programmers. Instead, operating system designers build high-level software tools in order to solve the critical section problem. The simplest of these tools is called a Mutex Locked. In fact, the term mutex is short for mutual exclusion. We use the Mutex Lock to protect critical sections and thus prevent race conditions. That is, a process must acquire a lock before entering a critical section. It then releases the lock when the critical section is exited. The acquire function acquires the lock, and the release function releases the lock. We can see this illustrated here. A mutex lock has a Boolean variable called available, whose values indicate if the lock is available or not. If the lock is available, in other words, a call to acquire succeeds, the lock is then considered unavailable. A process that attempts to acquire an unavailable lock is blocked until the lock is released. The main disadvantage of the implementation that we just gave is it requires what's called busy waiting. While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in order to call acquire. This continuous looping is clearly a problem in the real multiprogram system where a single CPU core is shared among many processes. Busy waiting also wastes CPU cycles that some other processes might be able to use productively. This type of mutex lock we have described is also called a spin lock, because the process spins while waiting for the lock to become available. Now, spin locks do have an advantage in that no such context switch is required when the process must wait on a lock, and a context switch may take considerable time. In certain circumstances on multi-core systems, spin locks are in fact the preferable choice for locking. If a lock is to be held for very short durations on one thread, it can spin on the process core, while another process performs its critical section on a different core. On modern multi-core computing systems, spin locks are widely used in many operating systems. Now, as we mentioned, Mutex Lock were generally the simplest synchronization tools that we can use, but a more advanced version of this is called a semaphore. A semaphore is simply an integer value that is accessed only through two atomic operations, wait and signal. Semaphores are just integer values, and operating systems generally distinguish between two versions of this, a counting semaphore and a binary semaphore. A counting semaphore can range over some unrestricted domain, so the counting semaphore can basically be whatever integer value. However, a binary semaphore can only range between the values 0 and 1. Therefore, binary semaphores are no different from a mutex. Now, counting semaphores can be used to control access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available. Each process that wishes to use a resource performs a wait operation on the semaphore. This thereby decrements the count. When a process releases a resource, it performs a signal operation, thus increasing the count. When the count of a semaphore goes to 0, all resources are being used, and after that, processes that wish to use the resource will block until the count becomes something greater than 0. For example, consider the two concurrently running processes P1 with this following statement and P2 with that following statement. Suppose that we require that S2 be executed only after S1 has completed. We can then implement this scheme readily by letting process 1 and process 2 share a common semaphore called sync. We assume that this is initialized to 0, and as we can see here, we insert inside of process P1 the command signal and P2 the signal to wait. Now, although semaphores provide a convenient and effective mechanism for process synchronization, unfortunately, such timing errors can still occur when we have mutex locks or semaphores. Let's suppose that we have a program interchanges the order in which wait and signal operations on the semaphore are executed, resulting in the following. In this first situation, several processes may be executing their critical sections simultaneously, which violates mutual exclusion. This error may be discovered only if several processes are simultaneously active in their critical sections. Note that this situation may not always be reproducible. Let's look at another one. Let's suppose a program replaces the signal with wait, so that it executes like this, a wait followed by a wait. Now in this case, the process will permanently block on the second call to wait. And finally, let's suppose that a process omits the wait or the signal, or maybe both. In this case, either mutual exclusion is violated or the process will permanently block. These are just some examples that illustrate the various types of errors that can be generated very easily when programmers use semaphores or mutex locks incorrectly. One strategy for dealing with such errors is to incorporate simple synchronization tools as high-level language constructs. Now we introduce the monitor type, which is a high-level synchronization construct. Now, an abstract data type, an ADT, encapsulates data with a set of functions to operate on the data that are independent from any specific implementation of the data. In relation, a monitor type is an abstract data type that includes a set of programmer-defined operations that are provided with mutual exclusion within the monitor. Now, this means a function that is defined within a monitor can access only those variables declared locally within the monitor and its formal parameters. Similarly, the local variables of a monitor can be accessed by only local functions. Here's one way we can visualize what a monitor is. The monitor construct ensures that only one process at a time is active within the monitor. Consequently, the programmer does not need to code this synchronization construct explicitly. However, the monitor construct, as defined so far, is not sufficiently powerful for modeling some synchronization schemes. For this purpose, we need to define additional synchronization mechanisms. These mechanisms are provided by the condition construct. A programmer who needs to write a tailor-made synchronization scheme can define one or more variables of the type condition. We define these as x and y respectively. The only operations that can be invoked on a condition variable are wait and signal, such that x.wait means that the process invoking this operation is suspended until another process invokes signal. And signal resumes exactly one suspended process. If no process is suspended, then signal operation has no effect. Now let's suppose when x calls signals, there exists a suspended process q associated with the condition x. Clearly, if the suspended process Q is allowed to resume its execution, the signaling process P must wait. Otherwise, both P and Q would become active simultaneously within the monitor. We can now see how the monitor can be augmented using these condition variables. Now let's consider the following scenario. X.signal operation is invoked by the process P. Now there exists a suspended process Q associated with the same condition X. Clearly, if the suspended process Q is allowed to resume its execution, the signaling process P must wait. Otherwise, both P and Q would be active simultaneously within the monitor. We know this can't happen. But now we're in a scenario where conceptually both processes could continue their execution, and so these two possibilities exist. We signal and wait, so P either waits until Q leaves the monitor or waits for another condition. Or otherwise, signal and continue. This is where Q either waits until P leaves the monitor or waits for another condition. There are reasonable arguments in favor of adopting either one of these solutions. On one hand, since P was already executing in the monitor, the signal and continue method seems more reasonable. But on the other hand, if we allow the thread P to continue, and then by the time Q is resumed, the logical condition for which Q was waiting may no longer hold. A compromise between these two choices exists as well. When the thread P executes and signals an operation, it immediately leaves the monitor, and hence Q is resumed immediately. There's a lot of programming languages that have incorporated the idea of monitors, and these include Java and C#. Now, another detail in using a monitor is how do we resume a process within the monitor? If several processes are suspended on the condition X, and the function xSignal is executed by some of those processes, then how do we determine which of the suspended processes should be resumed next? Now, one simple solution is to use a first-come, first-served ordering. In many circumstances, however, simple scheduling is not adequate. In these circumstances, the conditional wait construct has to be used. Now, in this version, this C is an integer expression that is evaluated when the wait operation is executed. The value of this C, which is called a priority number, is stored with the name of the process that is suspended. When xSignal is called, the process with the smallest priority is resumed next. Liveness refers to a set of properties that the system must satisfy to ensure that a process makes progress during their execution lifecycle. A process waiting indefinitely under these circumstances just described is an example of liveness failure. There are many different forms of liveness failure. All are generally characterized by poor performance and responsiveness. A simple example of liveness failure is an infinite loop. A busy wait loop presents the possibility of liveness failure, especially if the process may loop an arbitrary long period of time. Efforts at providing mutual exclusion using tools such as Mutex Locks and Semaphores can often lead to such failures in concurrent programming. Now, this can lead to pretty severe problems. For instance, the implementation of semaphores with a waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused by one of the processes on the waiting queue. Now, this type of scenario is referred to as a deadlock. We can see this illustrated here. So now let's suppose that we have two processes, P0 and P1, both accessing two semaphores, S and Q respectively. Let's assume that S and Q were set to the value of 1. Now let's suppose that process P0 executes a wait on the semaphore S, and the process P1 executes a wait on the semaphore Q. When process P0 executes a wait on the Q, it must wait until process P1 executes a signal on Q. Now similarly, when process P1 executes a wait on semaphore S, it must wait until process P0 executes a signal on S. Since these both signal operations cannot be executed, P0 and P1 are deadlocked. The values of the semaphore were 0, so both of these are going to block indefinitely. Now we say that a set of processes is in a deadlock state when every process in the set is waiting for an event that can be caused only by another process in the set. The events with which we are mainly concerned with are the acquisition and the release of resources such as mutex locks and semaphores. The liveness problem is also known as a priority inversion, and it can occur only in systems with more than 2 priorities. Typically, a priority inversion is avoided by implementing a priority inheritance protocol. According to this protocol, all processes that are accessing resources needed by a higher priority process inherit the higher priority until they are finished with the resource in question. When they are finished, their priorities revert to the original values. In this chapter, we have presented several synchronization problems that are introduced in multi-program systems. We have also introduced a number of tools that can be used to address each one of these problems. With all that being said, I'll see you next time.